we want to look at this compound called calcium carbide, okay? Okay, so we've got carbide, an IDE ending. We've got calcium that we know is Ca2 plus, and carbide. You guys have heard of carbide lamps. This is the chemical that's in those, and it's C2 2 minus. Okay, so it's kind of a polyatomic ion. And so we want to know if this calcium carbide or this carbide is stable. Okay, and so we're going to use MO theory to explain if it's stable. So is there a bond between these two things? And if so, how stable is it? And so when I look at this, right, I can tell there's a carbon that's bonded to a carbon, and there's a -2 charge, so it has extra electrons. And so I can either say, well, this one has the 2 extra electrons, or I can say this one has the 2 extra electrons, or I can say, oh, well, actually, I'm just going to make them so they're equal. So each one has an extra electron. And so I'm going to use this one because it's just easier. I don't have to think about the Z effective as much as if they're exactly the same. Okay, and so the electron configuration for carbon is 1s2, 2s2, 2p2, but there's 1 extra electron, so it's a 2p3. Okay, and so same thing over here, 1s2, 2s2, 2p3. So I have these 2 carbon or carbide, C minus. Well, it's, yeah, carbon with a minus. I'm trying to think of the name exactly. I have these 2 carbons with minus, right? And so to form a bond between these two, I need the orbitals to combine. I need to be able to add these orbitals together, okay? And electrons need to be in those orbitals when I combine them. And remember, I can only combine orbitals if those 2 things have to be true. The orientation is right, and the energy must be close. Okay, so if I go to the next slide, right, because these 2 are exactly the same, right, I've taken and put my orbitals in here at the exact same energy. So here's my energy, must be close. So when I know when I'm looking at these, the s orbitals have the same energy and the p orbitals have the same energy. Okay, and so I've got my atomic orbitals on the side, and I'm going to combine with my molecular orbitals to form this molecule. So energy-wise, like I said, you know, my s orbitals can combine with each other, and the p orbitals can combine with each other because they're close in energy. So next thing I want to check is the orientation. And so when I'm looking at this, remember I've got an s orbital, that's the circle. And remember that nucleus is, I don't know why that erased, and that nucleus is right in the middle. And a 2s orbital is a little bit bigger. Right, and then I've got the px orbital that looks like this. I've got the py orbital that comes in and out of the board. And I've got the pz orbital that's up and down. Okay, so I'm going to get out my pillow again. So here's my p orbital, right? I've got the px orbital that's this way in line with the paper. I've got the py that's coming in and out of the board. I've got the pz that's up and down. Okay, and so I've got that on one of my C minus atoms or ions, and I've got another set on this one. Okay, so imagine 2 of these pillows right next to each other, and these orbitals, you know, we're going to think about how they combine. Okay. So what I want to do, I'm going to skip this one. I drew all that stuff on the last one. I want to think about possible overlaps, okay? And I'm going to start with thinking about sigma overlaps. So to do that, I'm going to take the molecule and I'm going to draw an axis. And here I've got my X and here I've got my Z. And remember, the Y comes in and out of the board. And I put one carbon atom, and I'm going to orient my other carbon atom on that x-axis. Okay, so these two are kind of right next to each other. You can do any axis, right? I put the two carbon atoms next to each other and I draw the axes. And so when I draw it this way, here's my three little dots, meaning therefore, the 2s orbital will overlap. And they'll always overlap, right? They're just these big spheres. And the px orbitals will directly overlap. Okay, and remember px is on that x-axis, looks like this. Okay, so I'll start off by drawing the 2s orbitals. So the 2s, right, I have the s here, an s orbital here. When I add them together, they combine and form that one big bonding s orbital. Okay, with the nucleus in the middle and the electron clouds going around the two. Okay, then I do the 2s anti-bonding orbital. That's where I take the s orbital, I subtract them. When I subtract, it changes the color. And I get this orbital that is anti-bonding, where the nucleus is here and here in the middle of that, and there's a node down the middle. Okay. For my sigma 2p orbital, right, I take the x orbital, and I combine it or add it together with another px orbital. Okay, so here I've got my pillow, right? I'm taking the px that's on this one and I'm bringing them together this way. Okay, and so when they come together this way, it's a sigma overlap because they're headed end on. Okay, it's like putting two fists together. So this one, now the two colorless parts, I guess, combine to form a big part where the electrons want to be. And then I form these little parts at the end. Okay, and my nucleus is right there and right there. Okay. And so that gives me a sigma or a bonding p orbital. And I want to point out, you guys, that it doesn't matter if I have the color at ends on the inside or the outside. The colors just have to be the same for these to add. Okay, so I could take and leave the outsides uncolored and color the whole inside in. They just have to be the same color. Okay, so now we've got a sigma anti-bonding 2p orbital. And this is where I take the px. I'll just keep the coloring consistent. But this time I'm going to subtract these two orbitals. When I subtract, the phases change. And so I color the other side. So when I just started laughing, you guys. My Alexa just started talking to me and I have no idea why. I guess she wanted to talk about orbitals too. Okay, so here I've got the non-colored and the colored part. When they come together, they're going to form an anti-bonding orbital. Okay, and this is where I take, let me draw it out. And these two sides push away from each other. which pushes electron density into the lobe on the outside, okay? And so right here, electron density can exist, and so we get a node. So a node is where electrons can't exist. Okay, so there's my sigma orbitals, my possible sigma overlap. The balls, they can come together in any orientation. So if you have a 1s or a 2s orbital, they'll always be sigma overlapped. Okay, the 2p orbitals, like you have to have them come end on like this in your 3 dimensions. And the colors, if they're the same, they can combine. If the colors are different, then they push away from each other. Okay, so those possible sigma overlap. I want to do possible pi overlap. Okay, and remember pi overlaps is side-on overlaps. Okay, so let's say I take the pz orbital. So if I take the z orbital, it looks like this. And I bring it in with another orbital, that's a pz orbital, it looks like this. And I add these two together, I get this new orbital where, so here's my nucleus, right? My 2 nuclei are close to each other, and then the top parts of the clouds combine, and the bottom parts of the clouds combine. Okay, so it looks like that. And there's a node in the middle. And so this is my pi orbital. Okay, now I can take these 2 pz orbitals and I can subtract them, right? Because if I add something, I have to subtract it. When I subtract it, my colors switch, these phases, okay, switch. And when I combine these, this part is going to repel that part. So I still have my nucleus in the middle, but this time, instead of combining to form a cloud, it pushes itself away. Okay, and same thing over here, it pushes itself away. And so this is called my pi anti-binding orbital, or you can think of it as the PUZ pi anti-bonding orbital. Okay, and the p orbital looks exactly the same. But it's rotated. So it's rotated 90 degrees to come out of the board. So here, let me get my pillow out. Right, so before we were talking about the sigma bonds, they come this way, right? The pi bonds, now we look at the d orbitals. And the d orbitals, when they come together, right, they touch right here and right here, or they push away from each other. Let me go back to that slide. So they push together, right, or they come back out. And so PZ is when it's oriented along the z-axis. And then the PY one looks exactly the same, but it's rotated 90 degrees in and out of the board, right? So now these two can either overlap at the front, or they can repel each other depending on if we add the wave functions or subtract the wave functions. Okay, so that's kind of like what it looks like. So now we want to draw the diagram of this, right? And so I've got my carbon with a minus and my carbon with a minus here. And I've taken the 1s off the bottom because they're like, those orbitals are really close to the nucleus. And sometimes people include them, sometimes they don't. But the 1s is going to look exactly like the 2s, okay, if the questions ask you to draw those 1s. Okay, so here we've got electrons in the 2s, and then we've got electrons in the 2p, xyz, and same over here. Okay, so that's what it looks like, and remember the 1s is at the bottom. And so when I overlap these to form this C22 minus, I need to think about how these orbitals overlap each other. And PZ is this way, and S is the circle, right? So I have the 2s, these two come together. I have where they subtract each other, and I have where we've added them. And like I said, sometimes you'll see these as dotted lines. I'm going to draw them as a solid line because I think it's sometimes easier to see. So when I add them, it forms the sigma bond. It looks like that. And when I subtract them, it forms the anti-bond, which looks like this. Okay, so I've taken and added those together. Now for this part, we've got two different types of bonds, right? We've got the sigma bond and we've got the pi bonds, right? And so these two have different overlaps, and the better the overlap is, the lower the energy is going to be. Okay, so in carbon, when I draw this overlap, the pi bonds overlap better than the sigma bonds. Okay, so I'm going to go down, and I draw two pi bonds. And when I add them, I also have to subtract them. So they go up here. And these are my pi antibonds. Okay, next I have my sigma bond. So the sigma bond is when they're end on, the pi bonds are when they're side on. Okay, and I come down here and I draw my sigma bond. And sometimes that's called a sigma p bond, just to let you know that it's the p orbitals that are forming it. And for this one, and I'll explain in a little bit why, I'm going to draw this sigma bond up at the top for the sigma anti-bonding orbital. Okay, so if you click back through the slides, you can see what all these pictures look like, right? The pi bonds are side on. And so here we've got these two orbitals that have the nucleus with one electron cloud at the top, and it's all the same orbital, right? So this is where we have the Z orbital when they're up and down this way, and then the Y orbital when they're in and out of the board, and they line up, okay? The sigma is where they go end on. Let's see if I can draw that over here. So that's where we take the px orbital. Oops, I should draw that really big, and a px orbital, and I add them together, and I get this shape that looks like a piece of candy, right? But I've taken the two ends and stuck them together. Okay, so I have this orbital diagram. The last thing that I want to do is go through and add my electrons, right? And so you can do it two different ways. You can count up all the electrons on the side, or you can kind of look at it stepwise. So here I've got 2 electrons in my 2s and 2 electrons in my 2s. So there's 4 electrons total. So I'm going to bring those down. Maybe I should switch colors. Will that help? I'll go to purple. So I've got 2 electrons, 2 electrons. So I'm going to take and put 1, 2, 3, 4 electrons there. Okay. Now for this carbon, I've got 1, 2, 3, 4, 5, 6 electrons. So here I'm going to put 1, 2, 3, 4, 5, 6. Okay. So now all of my electrons are in my molecule. Okay. I've taken and combined 1, 2, 3, 4 orbitals on one side, 4 orbitals on the other. So I have 8 total orbitals. So in my molecular diagram, I have 1, 2, 3, 4, 5, 6, 7, 8, or 8 seats for electrons to sit. Okay, so your electrons always fill from the bottom. Okay, so then, you know, we ask like, so here's just another drawing of the same thing. I was going to put my electrons in. I guess I can put them in here. Right, so I had my electrons on the outside and I filled it in here. And we drew this diagram right here to figure out, is this molecule stable, right? So now I've drawn it. Let me calculate the bond order. Right, because the bond order, how many electrons are in between the two carbon atoms, is going to tell me how stable this is, right? So if you remember, bond order equals 1/2 times the bonding electrons minus the anti-bonding electrons. So bond order for this equals 1/2 times bonding electrons. My bonding electrons are you see that yellow? 1, 2, 3, 4, 5, 6, 7, 8. So I have 8 bonding electrons. And for anti-bonding electrons, we'll use orange. And anti-bonding, I have this in that anti-bonding or star level. So -2. So my bond order equals 1/2 times 8 minus 2, which is 6. So bond order equals 3. So if I were to draw the structure of this, I would have a carbon triple bonded to another carbon with 2 extra electrons, right? And so is this carbide stable? Well, it has a triple bond in it, so it's actually very stable, right? So again, if I look at this, like all my electrons have paired, so this is a diamagnetic compound. All electrons have pairs. Okay, and there's a triple bond. So is it stable? Yes, it's very, very stable. Are there any questions about this one? I think the important thing to kind of remember is every single line is a shape, and that shape can hold electrons. And so it's kind of cool. You can like look up different orbitals that just get really crazy as you add these wave functions together, add these shapes together, right? They're probability maps of where electrons can exist.